let's discuss the concept of pipelining and how this pipelining approach can improve the performance of instruction execution. For that, first consider the non-pipeline approach in which our processor is a single independent unit which will perform the instruction execution, which will fetch the instruction, decode it, execute it, and write back it. We are not organizing the processor into separate independent units where each unit handle each phase. Assume the time taken for each phase is 10 nanoseconds. This is not true. Usually the time taken for each phase may vary, but the pipelining method gives it best performance in case each of its subtasks take same amount of time. So first of all, we shall consider this ideal case in which the pipelining gives the best performance. For that, assume the time taken for each phase is 10 nanoseconds. We have 5 instructions to process. In non-pipelining approach, the processor starts fetching instruction I1. When I1 fetching is over, I1 will be decoded, then I1 will be executed, then I1 will be written back. So after 40 nanoseconds, instruction I1 is processed out. In non-pipelining approach, after processing instruction I1, processor will start fetching the next instruction I2. Now I2 is being fetched. After 10 nanoseconds, I2 is being decoded, then I2 is executed, I2 is written back. So again after 40 nanoseconds means at 80 nanosecond we get instruction I2 out. And after processing instruction I2, I3 will be fetched, decoded, executed and written back. The time taken is again 40 nanoseconds. So at 120 nanoseconds, I3 is processed out. Again after 40 nanoseconds, at 160 nanoseconds, I1 processing is over. And at 200 nanoseconds, I5 processing is over. So what is the total time taken to process these 5 instructions? 200 nanoseconds. The number of instructions into number of phases into time taken for each phase. 5 into 4 into 10, 200 nanoseconds. Now, if we are using the pipelining approach where we organize our processor into separate independent units, where each independent unit take care of each phase independently. We have 5 instructions to process. Our independent fetch unit will start fetching the instruction I1. After 10 nanoseconds, I1 fetch will be over and I1 will move to the independent decode unit to be decoded. Then our fetch unit, which is completely independent of the decode unit, is free now. So why should we keep this unit idle? We can start fetching the next instruction I2. So after 20 nanoseconds, I1 decode will be completed. At the same time, I2 fetch will also be over. After 20 nanoseconds, I1 will move to the execute unit. I2 will move to the decode unit, and the fetch unit, which is free now, can start fetching the next instruction I3. So now we are processing 3 instructions at the same time, and after 30 nanoseconds, I1 will move to the write back unit, I2 will move to the independent execute unit, I3 will move to the independent decode unit, and our independent fetch unit is free will start fetching the next instruction I4. Now we are processing 4 instructions at a time, and after 40 nanoseconds, I1 will be out, I1 processing will be over, and we will get instruction I1 out. At that time, I2 will be in the write back unit, I3 in the execute unit, I4 in the decode unit, and the fetch unit, which is free, can start fetching the next instruction I5. So here at 40 nanoseconds, we get the first instruction I1 out, similar to the non-pipeline approach. But the next instruction completion requires only 10 more nanoseconds, means after 10 nanoseconds or at the time 50 nanoseconds, we are getting the next instruction I2 out. Then I3 will move to the write back unit, I4 will move to the execute unit, and I5 is decoded. Again after 10 nanoseconds means at 60 nanosecond time we will get instruction I3 out. Now I4 is in the write back unit and I5 is being executed. Again after 10 nanoseconds we'll get instruction I4 out. Now I5 is being written back. After 10 nanoseconds mean at the time 80 nanoseconds we get 8 instruction I5 out. Thus, in non-pipelining approach, we get the first instruction out in 40 nanoseconds. Same with the case of pipelining. The first instruction is out only at 40 nanoseconds. Mean to fill the pipeline, it takes some time. Then here in non-pipeline approach, in every 40 nanoseconds, we are getting one instruction out. But here in every 10 nanoseconds, we are getting one instruction out, where 10 nanoseconds is the time taken for each phase. In other words, we can say in non-pipelining approach here within 80 nanoseconds we are processing two instructions. At the same time in pipelining within 80 nanoseconds we are processing 5 instructions. Means the number of instructions that can be processed within a span of time or within a period of time is more in pipelining compared to non-pipelined approach. The number of instructions that can be processed within a span of time, it is the throughput. So the throughput in pipelining is more compared to the non-pipelined approach. Hence, pipelining gives better performance in terms of throughput. Also, in other words, we can say here, if we consider each individual instruction, the time taken for each individual instruction is actually the same in both non-pipelining and pipelining. Every instruction has to pass through all these phases: fetch phase, decode phase, execute, and write back phase. Hence, time taken for each individual instruction is 40 nanoseconds. Even then, within a span of time, we are getting more instructions out in pipelining compared to non-pipelining. Hence, for n number of instructions, the time taken in pipelining is less compared to non-pipelining. Here for 5 instructions, the time taken is only 80 nanoseconds, but in non-pipelining, for 5 instructions, it took 200 nanoseconds. Hence, if we consider the execution of n number of instructions, there is a speed up in pipelining compared to non-pipelined approach. But this throughput and speed up are all dependent on the efficiency of pipelining. Also, we can see here to fill the pipe, it will take some time. But once the pipe is filled, then every subunit will be handling its subtask parallelly. Hence, if the number of instructions to process is more, then this delay to fill the pipeline will become negligible. Hence, efficiency of pipelining also depends upon the number of instructions to process. And again, here we consider the ideal case in which each subunit takes same amount of time or each phase takes same amount of time. But usually, each phase take a different amount of time. And there are some additional interstage delays which will also affect the efficiency of pipelining, which we'll discuss in the next video. So in general, pipelining makes use of the method of parallelism to provide improved performance compared to the non-pipeline approach. And the performance of pipelining can be in terms of throughput, which is the number of instructions that can be processed within a span of time, or in terms of speed up. The speed of execution of n number of instructions is more in pipelining compared to the non-pipeline approach, and this throughput and the speed up depends upon the efficiency of pipelining. If the pipelining is 100% efficient, then we can attain maximum throughput and maximum speed up. But in practical scenarios, this 100% efficiency is not possible. Hence, the maximum throughput and the maximum speed up cannot be achieved, but the target will always be to approach the maximum throughput and maximum speed up.